Welcome. This video is intended to help you recognize and factor perfect square trinomials with ease. So let's look at first a couple of things that you should remember from the last time we worked on polynomials. As we look at what we did in the past, we have here x minus 3 quantity squared, which we should remember means we're going to take x minus 3 and multiply it times itself, x minus 3. Now, under FOIL, we know that we needed to take our first terms, x times x, and that should give us x squared. We need to take the outside terms, x times negative 3, and that should give us negative 3x. We need to take our inside terms, negative 3 times x, and that should give us negative 3x. And then, of course, we take our last terms, negative 3 times negative 3. And when we take our last terms, that gives us plus 9. Simplifying by combining like terms, of course that gave us x squared minus 6x plus 9. Now, there were some shortcuts that we should have been able to figure out. For example, we should recognize the negative 3x appeared twice. And it makes sense because the negative 3 appears twice and the x appears twice. So that should happen twice. Additionally, we should have been able to easily predict this x squared value, because that's the first terms, and this 9, because that's the last terms. This is what created a perfect square trinomial. Let's see how that looks with this one. Again, I see that this is x plus 4 quantity squared, which to me means I have an x plus 4 multiplied to itself, x plus 4. Now, knowing what I know about FOIL, I'm going to take the first terms, x times x, which will give me x squared. I'll take the outside terms, x times 4, that will give me 4x. I'm going to take the inside terms, that's 4 and x, and that will also give me 4x. And I'll take the last terms, 4 and 4. When I multiply those out, I get positive 16. Again, simplifying by combining like terms, I'll get x squared plus 8x plus 16. Again, that was very predictable. I should see the 4x plus 4x is 8x because 4 times x and 4 times x always will give me that twice. And the first term, x times x, is very predictable, x squared. And the last term, 4 times 4 is 16, very predictable because we expect that to happen every time. In fact, so predictable are these patterns that we don't actually have to show the multiplication for them. When I see any polynomial, any binomial being squared, I know that I can immediately say the first term will be a squared, because that's a times a, that the middle term will be 2 times a times b, or 2ab, and that the last term will always be b times itself, or b squared. Now the only thing that changes slightly is when I'm using an a minus b quantity squared, I know the first term will still be a squared, because that's a times a, but the middle term, a times negative b, will be negative 2ab, and negative b times negative b, a negative times a negative is always positive. So I get plus b squared. In fact, the only thing that's different between what I have in the first one and what I have in the second one is this. On the first one, I have a plus because the original binomial had a plus, and on the second one, I have a minus because the original binomial had a minus. These identities become extremely important in math. So now let's look at this trinomial. This trinomial is a perfect square trinomial, and it's one I can easily factor. Now here's the things that we have to go through to analyze whether or not something is a perfect square trinomial. First, I look at this first term. Is it a perfect square? In this case, yes, it is a perfect square. Then I move to the last term. I look at the 9 and I ask myself, is this a perfect square? Well, 9 is 3 times 3. So yes, that is a perfect square. I'm well on my way to being able to solve this using perfect square trinomials. The last thing I need to analyze to determine if it's a perfect square trinomial is right here, plus 6x. Because I need to figure out if this 6 is 2 times whatever I multiplied to get x squared and whatever I multiplied to get the 9. Well, to get x squared, I must have had x times x. To get the 9, I must have had 3 times 3. So I ask myself, is x times 3 times 2 6x? And yes, it is. So that tells me that this is a perfect square trinomial because the first one is a perfect square, the second term is 2 times a times b, and the third one is a perfect square. I can automatically factor this very simply as x plus 3 quantity squared. Now let's analyze this one. I have the first term of x squared. Is that a perfect square? Yes. The square root of that is x. I'm looking at the last term, positive 16. Is that a perfect square? Yes. 4 times 4 is positive 16. So now I know that that would have been a 4. But here's where I need to ask myself, is x times 4 times 2 8x? It is. This again is a perfect square trinomial. And it can be easily factored as the x from the first term, the 4 from the third term, squared, and then I just have to look at what do I have in the middle. In this case, it's a minus. So I know that there is a minus here in the problem. This would factor as x minus 4 quantity squared. So now let's look at some other examples of trinomials that may or may not be perfect squares. And we're just going to analyze them the same way we have. On A, the first term is a perfect square. The third term is not. This cannot be a perfect square trinomial because the first and the third term are not perfect squares. On B, this looks promising. I have a first term that's a perfect square. I have a third term that's a perfect square. 36 is 6 times 6. That's a perfect square. But now I have to analyze this middle term, 6x. Well, I know the square root of x squared is x, and the square root of 36 is 6. This says 6x, but what I have to remember is I have to do x times 6 times 2 to get this middle number. I should have seen a 12x here, not a 6x. This is, in fact, not a perfect square trinomial. Now let's look at the last one. Hey, look, perfect square. X squared is a perfect square. That's awesome. Oh, and right here, a 36, except for one problem. Right here, I can see that this is a negative 36. No negative is ever a perfect square. In fact, you cannot get a negative perfect square. This has to be a positive number for the third term to be a perfect square. So, since the third term is actually not a perfect square, this is also not a perfect square trinomial. The only way to have a perfect square trinomial is to have a first term that's a perfect square, a third term that's a perfect square, it's positive, and for the middle term to be 2 times the square root of the first times the square root of the second. Or, in this case, 2 times x times the square root of 16, which is 4, which gave me the middle term of 8x. If that's what I have, I can factor it as x plus 4 quantity squared and be done. So now it's your turn to kind of analyze this. Look at the problem that I have here. The first term is obviously a perfect square, and the third term is obviously a perfect square. What we need to do is figure out what value should go here that would make this a perfect square trinomial. Pause the video for a second to determine what value you would put there. The correct value that should go in that space that makes this a perfect square trinomial is 14x. I get that because the square root of the first term is x, the square root of the third term is 7, but I have to remember to multiply it times 2 to get the 14x. Look at this problem. Again, this could form a perfect square trinomial. The first term is a perfect square, x squared. The third term is a perfect square, 144. Your job is to determine what value goes here in the middle that would make this a perfect square trinomial. Pause the video for a second while you contemplate that. The correct value that goes in the middle is 24x. Now I got that because the square root of the first term is x, the square root of the second term is 12, but I have to remember to multiply it by 2. 12 times 2 times x is 24x. How about this last one? Well, there's one more after this, but it's a little more challenging. Look at this one. Please figure out what value has to go here in the middle to make this a perfect square trinomial. The correct answer is 22x. Again, I got that because the square root of the first term is x, the square root of the third term is 11. When you multiply that times 2, you get 22x. So that is what the middle term would be. Here's one that is very much more challenging. Again, in order to use the perfect square trinomial factoring method, I look at the first term. Is it a perfect square? Well, 4 is a perfect square, and x squared is a perfect square. So yes, it is, and it has a square root of 2x. I look at the last one. 81. It's positive, and 81 is a perfect square. That's 9 times 9. So now I ask myself, 2x times 9 times 2. 18x times 2 is 36x. Now, under normal circumstances, I would have to use factoring by grouping to solve this thing. And I have to say that 4 times 81 is 324, and I'd have to find two numbers that would multiply to 324 and add to 36, which would be 18 and 18. Then I'd have to replace the middle term, and oh, it's just much more work than I want to do. Instead, since I can see that this is a perfect square trinomial, I'm going to simply write the square root of the first term, the square root of the last term, and then whatever symbol is in the middle, which in this case is positive, goes in the middle, and I'm done. So to summarize, if we have a trinomial in the form a squared plus 2ab plus b squared, we can easily factor it as a plus b quantity squared. And if we have a trinomial that says a squared minus 2ab plus b squared, we can easily factor it as a minus b quantity squared. We don't have to go through the whole process of factoring by grouping if we can recognize the patterns.